Is that the last one?
Maybe not.
Ah.
Maybe not.
Yeah, we only have.
All right. So the last thing we covered was the body stability criteria. Remember what it involves. A body plot of the product of all transfer functions in the loop.
Do you have another one of those?
And then it's very simple. Very simple. You have the dual plot of log amplitude ratio, which is the magnitude. I remind you that amplitude ratio is the magnitude of the transfer function we're taking the body plot of. And so far we have been the GOL, product of everything in the loop, at I omega. I'm just putting here G because, as we'll see today, there will be reasons to do body plots of different transfer functions. And for the stability criterion, we find where the phase lag is minus 180 degrees, and move to the left until we hit the phase lag. The frequency at which phi is minus 180 is the crossover frequency. And then we go up or down. So in that frequency, we find log amplitude ratio. In this case, you go up, and then you go left. So this is the path to do. And if this intersects where AR is less than 1, log AR negative, then we are closed loop stable. If it intersects when log AR is positive, we are closed loop unstable. So if less than 0 is the log scale stable, greater than 0 unstable. Recall though that there is a very important condition for the body stability criterion. It's for the garbage can, totally meaningless, doesn't say anything about the closed loop system if the system is open loop unstable. So that's a critical condition. So the very first thing you need to do before using body stability criterion always is check if you have open loop stability. And what's the easiest tool to check for use for open loop stability?
That table?
Routh array, exactly. Okay? There's the second condition of having only one crossover frequency that rarely comes into play. Clear? Okay. During the break, I decided, totally optional, you can be enjoying your lunch if you're here. If you want to go and not hear it, fine. I will spend maybe 10 minutes to give you a quasi-proof of the body stability criterion. I decided I'm going to do it during the break, not include the class material, not be examining on this or anything, but if you are curious on a quasi-proof of that, I can spend about 10 minutes during the break to just go over, okay? All right. So far, what have we done in this? Well, we have learned how to get linear input-output models in the Laplace domain called transfer functions. We have learned how to do that both given a mathematical model by finding the nominal steady state, doing Taylor series expansions and linearizing and taking Laplace transforms. And we have learned also the practical way where we do small step changes and fit those step changes to transfer function models. If the transfer function model is first order plus time delay, we already have learned a controller tuning method, the Cohen-Kuhn method. If, though, I have inverse response or visible oscillations, or a maximum, a minimum, in those cases, first order plus time delay would not be a satisfactory fit. It would miss some important characteristics of the system. So it would be nice if we have a controller tuning method that can be used for any transfer function. And that's the first topic of today. We're going to talk about the Ziegler-Nichols method. As far as I know, no relationship to our Dr. Ziegler. Same story. So, this is a method that is based on a certain characteristic, couple of characteristics of every system. The ultimate gain and the ultimate period. So it's a method that plug and chug after obtaining ultimate gain u and ultimate period p. So we need to get a couple of system characteristics called the ultimate gain and the ultimate period. Once we have them, the tuning is this table here. If I have just P control, simply I have only one parameter for P control, for proportional control. So simply U prime equals KC error, the controller gain parameter, and that is obtained by taking the ultimate gain and dividing by 2. And there's no tau I, no tau I. Okay? For Pi, the Kc is reduced to Ku over 2.2, and the tau I is Pu over 1.2. There's no tau D. And for idea PID, the Kc is increased to Ku over 1.7. Tau I, Pu over 2. And tau D, Pu over 8. So that's where we are heading. And let me just double check that I didn't mess something up. So, what is the Ku and the Pu that we have plug and chug once we get Ku and Pu? Here is how an open loop stable system with just proportional control would respond as I increase the Kc, the controller gain, to a set point change. So if I have just P control, and I make a step change in the set point. So that's Y set point. And a little bit of orange. An orange is Y. How the system would respond? If Kc equals 0, how do you think the system will respond to set point change? Who will tell me? Meaning? Good? Meaning?
It doesn't change.
It doesn't change, exactly. If Kc is 0, U prime, which is Kce, P control, remember, is U prime of T, is Kc error. So if Kc is 0, this will just have U prime equals 0, U nominal value, so it will just continue being like that. So that happens if I have Kc equals. As I increase the magnitude of Kc with the appropriate sign, positive or negative, what will happen is I will start responding, but remember, we saw it very well also in the game, without integral action, you have steady state offset. So, as the magnitude of Kc, let's say after some delay, here would be for small Kc, if you increase the magnitude of Kc, you get closer to the set point. At some point, you start having oscillations. So, still further. So this is, I'm showing what happens as absolute value of Kc increases. And there will be a specific, okay, if I continue going higher, eventually I'll become unstable. So eventually what will happen is blown up.
You have positive P. Positive P, so you'll get that.
Yes, so the closed loop system poles become positive. Yes. Okay, so Kc equals 0, wouldn't respond at all. As I increase the magnitude of Kc, I will be coming closer to the set point. At some point, I will be coming closer with oscillations. Increasing further, eventually I'll become unstable. Yeah.
Why do the oscillations decrease at a certain point? Like the first row line here, but then the upper
Yeah,
line.
because when it's stable, the oscillations die out. Remember, when I have complex conjugate poles, what do I have in response? I have e to the minus AP cosine, e to the p real part, t cosine, p imaginary, p cosine. So that's the amplitude. If the real part is negative, the amplitude goes towards 0 and the oscillations disappear. If the real part is positive, the amplitude blows up, so you blow up in an oscillatory fashion. And there will be just one unique value of Kc where you are at the verge of instability, where you will get oscillations that don't blow up and don't die out. Okay? There's just one value of Kc with proportional control that will give us sustained oscillations. With me? So, that would be, here, let me draw an equation underneath. perpetual oscillations, never dying out, but never blowing up either. The value of Kc that causes that is the ultimate gain. So all this form are Kc absolute value less than Ku absolute value. This is Kc absolute value greater than Ku absolute value. Concept clear? Not convincingly. How about them? Okay. So that's the ultimate gain. We are using the ultimate gain to tune P, PI, or PID controllers, even though it's based on the characterization just with P control. One.
Can you give us like a numerical example? Because I have no idea what's going on.
Well, there's no numerical, this is all concept. So why would it be good to give you particular equations? Just understand that this is what is happening.
Okay.
If I have proportional control with magnitude less than Kc, than Ku, okay, the system will be stable, and first without oscillations, then with oscillations, dying out, you move to a new steady state, and as you increase the magnitude of Kc, you move closer and closer to the state. If you go too high though, you become unstable. There is a particular value where you don't blow up, but yet you never reach a steady state. It never dies out. That's the ultimate gain. Let me finish this, Felix. What about the ultimate period? Once initial, and on purpose I didn't draw the first oscillation the same as this oscillations, once the initial effects die out, then you have repeating oscillations. The period of those repeating oscillations is the ultimate period. So this period here is period.
Is that the same as the input? Is that the same as the input?
Well, the input doesn't even have a sign. The input is a step change.
Yeah,
The
but
input here is a step change.
you said like they were like the same on amplitude, input and output.
If the input is periodic, but here the input is not periodic.
Okay.
Felix, your question.
So let's say that we have a P controller. We can find that value by finding Kc and multiply by 2.
Well, no, you find Kc from Ku. You find the good control tuning from Ku.
So you,
Ku is what brings the best instability. So, conceivably, we could get these two parameters experimentally, right? We could be doing experiments. But let me explain exactly what is happening. What is happening is, here is imaginary axis, real axis, and for small values of Kc, unless the system has complex conjugate poles already, you will have, let's say, the dominant pole, the one next to it, will be both 8 and negative. As you increase the magnitude of Kc, those two poles would move towards each other, and at some point, they would take off being the complex conjugate, as complex conjugate poles, and start doing probably something.
What?
So I'm showing you what happens to the closed loop poles as I change the magnitude of Kc.